Hello all, now we are going to see basic pulse radar explanation for simulate, detect, and estimate target range. These content is sourced from the MathWorks website. This example comes from the radar and EW systems section. Let's get started. These contents are covered in this video. Although the MathWorks example includes various MATLAB codes and helper functions, I focused more on the theory and gave simplified explanations supported by relevant AI-generated images. These video tries to explain design a pulse radar system in simple terms. It shows how to design a pulse radar system from a set of user requirements, like I want to detect targets up to 5 kilometers away with certain reliability and resolution. It translates those requirements into actual radar parameters, waveform type, pulse width, transmitter power, antenna, etc., so that the radar works as intended. It then simulates the radar environment with targets, noise, signal propagation to produce a synthetic received signal. Finally, it applies signal processing, match filtering, pulse integration, threshold detection to that received signal to detect the targets and estimate their ranges. MathWorks Sutter's approach shows full chain, from design to simulation to detection. Good for understanding the why and how. Problem statement and design goals. Want to detect targets with radar. Given requirements. Max detection range equals 5,000 meter. Range resolution equals 50 meter. Minimum target radar cross-section, RCS, equals 1 square meter non-fluctuating target. Probability of detection, PD, equals 0.9. Probability of false alarm, PFA, less than or equal to 10 power minus 6 environment assumed. Free space, no clutter, no multipath. Detection method, non-coherent detection, less complex, no phase tracking, chosen for simplicity. Radar system, waveform and basic parameters. I use a rectangular pulse waveform, simple, easy to simulate, that a range resolution determines waveform bandwidth. For rectangular pulse, bandwidth left and right arrow pulse width. Bandwidth equals C by 2 into range resolution, and pulse width is equal to 1 by bandwidth B. Pulse repetition frequency, PRF, is chosen based on maximum unambiguous range. Sampling rate is set to twice the bandwidth, Nyquist criterion for sampling waveform. Receiver and transmitter setup. Receiver, assume only thermal noise, no clutter. Noise bandwidth same as waveform bandwidth. Receiver gain and noise figure are set. Example uses 20 dB gain, 0 dB noise figure. For simplicity. Transmitter, main parameter, peak transmit power. This depends on required SNI at receiver. Pulse width, so waveform bandwidth. Maximum range, target RCS. Antenna gain, wavelength, etc. Understanding detection requirements, senior transmit power. To meet PD equals 0.9 and PFA equals 1e power minus 6 with non-coherent detection, required senior is high, tilde 13 dB, according to ROC curve. But high senior, very large transmit power. Example says tilde 33 kilowatt, not practical. Solution. Use pulse integration, i.e. integrate many pulses, to reduce required senior. Example integrates 10 pulses. Required senior drops to tilde 5 dB. Then use radar equation plus the senior to compute usable transmit power. Example yields tilde 5 kilowatt, more reasonable. Antenna and environment setup. Use a simple isotropic antenna for simplicity. Operating frequency chosen. Example uses 10 GHz, gives wavelength for radar equation. Model environment is free space, and propagation as two-way delay, outgoing pulse plus echo return, from radar to target and back. Modeling targets and simulating returns. Define multiple targets. Give their positions, distance from radar, and RCS. Example uses 3 stationary targets to Ono target motion in example. For simplicity, 0 velocity. Propagation channel defined. Free space, two-way, so that echo delay matches actual range. Transmit, pulse, propagate, reflect, return, receive, with noise. Do this over multiple pulses, pulse train, to simulate realistic radar returns. Signal processing, from raw echo to range detection. The received pulses are sampled, fast time and slow time axes, forming a data matrix. Match filter convol the received signal with a time-reverse version of the transmit waveform improve senior processing gain. Because echoes from farther targets are weaker, path loss, their amplitudes vary with range. To correct this, a time-varying gain, range compensation, is applied so that all returns appear as if from same reference range. Then perform non-coherent pulse integration, e.g. integrate energy over 10 pulses, further improve senior. Finally, apply a threshold detector, based on noise statistics plus false alarm requirement, to detect peaks. Each peak corresponds to a target echo. Convert the time delay, position of peak in fast time, to range, using speed of light. The example detected ranges are within plus or minus few meters of true ranges within the 50 meters resolution. Summary. This presentation shows how a basic monostatic pulse radar can be designed from requirements, range, resolution, detection reliability, by choosing appropriate waveform parameters. It explains how pulse width, bandwidth, and pulse repetition define range resolution and maximum detection range. To reliably detect weak echoes, it introduces techniques like match filtering and pulse integration, combining multiple pulses to boost senior and reduce required transmit power. The demo uses these ideas to simulate radar returns, detect targets, and estimate their ranges. Thank you and meet you in next video. Bye.